So with this logic, basically you would be able to answer B and C here. Higher speed would be at Q, and there will be zero speed at P and your R. So just now we have talked about point number 2C. The higher the speed of the relative motion between the magnet and the solenoid, the greater the rate of change of magnetic flux, right? So since the higher speed is at Q, you would expect that it will give you the greatest rate of change of magnetic flux. So because of that, your induced EMF will be greatest at Q, and similarly, if you apply the same logic, if your speed is 0 at P and Q, it means that at that particular time, to the solenoid, the magnet is actually not moving because V equals to 0. So because V equals to 0, then there will be no rate of change, and so that particular instance, you would not be able to produce any EMF. Yeah, so the good thing about this way of producing electricity is that you just need to apply the force once, and then the spring should help the magnet to oscillate, and you will be able to induce current in the coil of wire, and you can use that to power up other components, right? But unfortunately, this will not give you a very consistent supply of induced EMF. Yeah. Okay, let's try one more question. This time round, it is not as straightforward as your question number 1, whereby it is basically really checking whether you can apply Faraday's law. So now there's a context added to this question. If I am able to return to school before we close for the semester, I can bring this toy and show you actually we made it, right? So what happened is that there's a tube, and in this tube you have a piece of magnet, that can slide left and right. So this magnet can actually go like that, and then if you shake it the other side, the magnet can go through like that. So in a way, the magnet is passing into the solenoid, right? Then out of the solenoid, and then when you shake it the other way, it will go back into the solenoid and out of the solenoid again. Why do we have this rubber padding? Is so that when the magnet hits this part, it will not break the tube, right? And outside the tube, there is a coil of wire, a solenoid, and then this solenoid is linked to a light bulb. So as you can see, this circuit doesn't have electrical source. So one telltale sign of an EMI question is that when you see that the circuit doesn't have an electrical source, you would know that it is about electromagnetic induction, right? So in this case, the magnet basically can go in, go out, go back in again, go out again. So because of that, this is a kind of like a vibration. And remember when we started with question number 2, right? We say that you need to be specific whether or not the solenoid or the conductor is experiencing increasing or decreasing magnetic flux, right? But because in this case the magnet is either going in or going away, so it is kind of like vibration. You cannot be so specific whether it's increase or decrease. So actually you can use the general term changing, right? So let's see whether you can fill it up yourself. So take a pause here and try to fill it in, and then after that we will have a check. Okay, pause the video. Okay, I hope you really follow my instruction and really pause the video. Okay, so what is the trigger condition of this induced current? And obviously you can find out from the context, right? The toy can only light up when it is shaken. So the trigger condition must be that it is being shaken. But you cannot just copy and pluck it out directly from the question's context. You need to rephrase it in terms of physics terms. So when you shake it, what happens? Well, basically the magnet is sliding up and down the tube, right? Sliding, tube is called tube. Sliding across the tube, right? And then what would happen? Basically the conductor, right? So what is the conductor here? The conductor here is the solenoid. right? So the solenoid will experience, in this case, changing because it is vibrating, right? It's sliding in and sliding out, right? Magnetic flux, keyword here, linking to what? What is the magnetic source? So the magnetic source here must be the permanent magnet, right? And by Faraday's law, remember it is induced EMF, right? You can say an EMF is induced across the circuit and light up the bulb, right? So I hope you have paused the video and you are able to fill in the blanks. So last but not least, I will end the video with the introduction of Lenz's law. So what is Lenz's law? If you think about Faraday's law, it only tells you that there's an induced EMF. But did it tell you in which way will the current be flowing? No, right? So basically Lenz's law settles that. So Lenz's law is very hard to understand what it actually mean just by reading out the law. So instead of that, I will just give you a scenario. This scenario is very similar to any boy-girl relationship in any Korean drama. So what is this analogy? So in most drama, you will see that let's say you have a boy and you have a girl. Let's say their relationship is rather stable. But one day, somehow the girl decided to be very, very sticky. So you always want to approach the boy. So what will the boy do? The boy will start to take the girl for granted and would want to resist her, right? He would want to repel her, right? And in another scenario, when the boy start to repel her, the girl will start to feel very disheartened, disappointed, and will start to, move away from the boy. And at this moment, the boy would then want to actually attract her back, right? And this analogy is basically what Lenz's law is trying to say. When the magnetic source is approaching the solenoid will want to create a magnetic effect that want to repel the approaching magnetic source. Okay, so let's put it into an example. So let's see. So I have a solenoid and I have now this magnet, and this magnet is moving away. So when the magnetic source is moving away, it's like the girl is moving away. So what would be the reaction of the male counterpart? Well, the boy will start to feel insecure and will want to do many things to get back the heart of the girl, right? Want to attract her back. So as you can see, it is the North Pole that is leaving, right? So how would the solenoid create a magnetic effect that will attract back the North Pole? Let's say here, I can create a pole. What pole should I create so that I can attract back my North Pole that is leaving me? Well, I would want to induce a South Pole here so that my North Pole that is leaving will be still attracted to me, right? So if I need to create a South Pole here, meaning that I have to create a North Pole here. And I hope you still remember your right hand grip rule. So if you apply your right hand grip rule, it should look like this, right? With the finger curling like this. This is the only way your thumb can point to here, right? So this will create the North Pole here. This means that the current have to flow this way, right? If the induced current flow this way, then you would be able to create this induced South Pole to actually attract the North Pole that is actually moving away. So basically Lenz's law tells you this, and once you apply Lenz's law, you can then see that the current must be like this, right? And so you know that 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 if you put a galvanometer there, you will see that the galvanometer will actually point this way. So a galvanometer basically tells you how the current will flow. If your I think I show you this in the lab, right? There is this meter. Maybe I show you here. So there is this thing here that start with a G. Yeah, maybe I picture this. So how does this work is that when you have, let's say, a wire here and a wire connected here. Yeah, maybe like that. A thick wire. Okay. If the current is going in like this, then the pointer will go this way, right? And if the current is going the other way, where is my undo button? If the current is going this way and out this way, the pointer then will go this way, right? So basically a galvanometer can tell you the amount of current and the direction of the current. So in this particular question, when we apply Lenz's law, after we determine the induced current, we can then deduce how the galvanometer will point, right? In another example, let's say this one. So let's say this one. So let's say now C, okay? Let's say C. Now the south pole is approaching, so meaning that the girl become very sticky. So when the girl become very sticky, the boy will take her for granted and want to repel this very sticky girlfriend in most Korean drama. So when the south pole is approaching, then what will the solenoid do? The solenoid will want to repel, right? So what is the pole that must be induced here to create a force of repulsion? So obviously, to repel a south pole, the best way is to create a south pole, right? So by the same logic, if you apply your right hand grip rule, in order to have this north and this south over here, the induced current must flow this way. And if the current were to flow this way, then the current in the circuit must flow this way, and then I know that my galvanometer will show me this kind of reading, right? So this is what Lenz's law says, right? If you have the permanent magnet approaching the solenoid will react in such a way that it will want to repel away this approaching north pole. And if you have a south pole that is approaching, then they will react the other way. So for your Lenz's law, it states that the direction of the particular induced current I think you will need to start with induced EMF first, and hence the induced current is such that is. So this is refer to this, right? So Lenz's law says that the direction of induced EMF and hence the induced current is such that the induced current's magnetic effect will oppose the motion or change that producing, what is this? The induced current. So for example, if you have a north pole approaching a coil, the induced current in the coil will then induce a south pole. It will induce a north pole, induce a north pole at the near end to oppose the approaching north pole. So what I want you to do is that I want you to try out A to F. F is particularly tricky. So if you want to try, you can try. If not, you can wait for me when hopefully when I can return in Tuesday. Okay. After this, I want you to try checkout activity 8 and 9, and then that's all for me today. If you still have remaining time, ya lor, use it to finish your checkout activities. Okay, I think my throat is hurting again, and please take care. COVID the second time is no joke, it's hell. So yeah, good luck and stay healthy.